Okay, let's go ahead and get started. All right. In today's lecture, we continue studying natural logarithmic functions, and it's a continuation of what we did last time. So let's just recall a few things. So last time, the main definition that we learned was natural log of x is equal to the integral from 1 to x, 1 to t, dt, and this is where x is greater than 0. Okay, this is the main definition that we introduced last time. Okay, and in studying this, we derived several properties of it. In particular, we were able to derive the derivative properties of this function. And we said, so there was like a star bullet point, right? It was that dx of natural log of u is equal to u prime over u, provided that function u is greater than 0 for all x in the domain of u. So here u is a differentiable function of x, and we derive this property. Now, in a similar manner, which will come up today, we also have that the derivative with respect to x of the natural log of absolute value of a function u of x. This is also u prime over u, but now there's no condition on u being positive. Okay, and that's because this absolute value kind of ensures that. Now, we also mentioned that the natural logarithmic function is monotone increasing, and it's positive for x greater than 1. So because this function is increasing, there is some value of x where natural log is equal to 1. And that's what we define the number e as. So that's a definition that we didn't get to last time. So the number e is the unique positive real number such that natural log of e is equal to 1. So that's how we define that exponential e number. Okay. Basically, if you plug in e here, this will evaluate to 1. There is such a number because when x is equal to 1, this is 0, and then for any x larger than 1, it's increasing. So eventually it's going to pass 1, and we define e to be that number. Okay. All right. So in this lecture, we're going to now move from derivatives of the natural logarithm to integrals of the natural logarithm. So these will be indefinite and definite intervals. So in order to do that, we need the following theorem. So I think this is theorem 5.5 in your textbook. And you'll notice this as we go throughout the semester that the way that I write the theorems is a little bit different than how the textbook writes them. I feel like the textbook sometimes has unnecessary bullets in their theorems, so I like to write them in the simplest way possible. So it looks different, but it's equivalent. So this theorem states that if u is a differentiable function of x, Then the antiderivative of natural log of u. Oh, sorry. 1 over u, sorry. Du is equal to natural log absolute value of u plus c. Okay. So now this solves the question, the very first thing that I posed in the previous lecture about how do we integrate or find antiderivatives of u to the power of -1, which is, that's what that is, right? Now, if I were to write this in terms of x, so notice that here the variable of integration is u. We can write this in terms of x, and this will probably be useful for you. So note that if u is a differentiable function of x, then du is equal to, well, let's write it out like this. An equivalent form is this. U prime over u dx is equal to the natural log absolute value of u plus c. So this is equivalent to this, and you'll see when we do examples that this will be the form that you use most often. Okay, so hopefully you can see why these are equivalent. So here, so u is a differentiable function of x. So if we take the derivative with respect to x, we get u prime dx equals to du. So that's all that's happening here. Right? Because maybe you'll recognize this. U prime is du dx. So if we write this like this, then we can replace that du with u prime dx, and you see that they're equivalent. Okay, so let's just, pretty much the rest of the lecture is going to be doing examples. That's kind of the nature of this section. So, yeah, let's go ahead and get started. So find the indefinite integral of 1 over 4x minus 1 dx. Now, this might not look like that or like that, but you'll see that we can make it look like one of these, in particular this one. So the way that I'm going to do that is I'm going to look at this and notice that, well, I'll write out every step of the solution here. So if I let u equal 4x minus 1, okay? If I let u equal 4x minus 1, then du, so we take the derivative on this side, and the derivative on this side is just going to be 4 dx. Right? Take the derivative with respect to x on this side, just have 4, right? So then du is equal to 4 dx. Are we clear on that? All right. It looked like Zoom crashed for a second. Hopefully it's still recording. Okay, can y'all hear me now?
Yes, sir.
Yes, you're good.
Okay, so here, if we assume that u is a function of x, which if I write u this way, it is, do you agree that du is equal to 4 dx? Do you understand how I got there?
Yes, sir.
Right? Because if you do du dx is equal to 4, then multiply both sides by dx in a sense. So now that I see this, right, I notice that this means that 1/4 of du is equal to dx. Okay? Now, you might be wondering why I'm doing all this. I'm trying to find this integral. Well, I have now this here, 4x minus 1, that's equal to u, right? So I can replace 4x minus 1 by u, and then dx is equal to 1/4 of du. So with that, I can now rewrite this integral of 1 over 4x minus 1 dx. I can rewrite this in terms of u. So this becomes the indefinite integral of 1 over u times dx. But dx is going to be 1/4 of du. That's just a constant, that fourth, so I can pull that in front of the integral. And now we have this form here. 1 over u du. 1 over u du. So we just apply this theorem. So it'd be 1/4 times natural log absolute value of u. Plus your integration constant, right? But we're not done. We were asked to find this integral in terms of x. This is in terms of u, but what is u? It's 4x minus 1, so we just substitute back in. So finally, we get 1/4 natural log absolute value of 4x minus 1. Let's see. And this will be the final answer. Okay. And this procedure is going to repeat over and over and over again. Basically, the idea is to look at your integral and see if you have u in the denominator and u prime in the numerator, right? So u prime in this case was, we had this 1/4 dx business on top. So the best way to really understand it, I feel like, is just to do a bunch of examples. So let's keep on doing that. So now we'll do one with a definite integral. So find the area of the region bounded by the graph of y equals to x over x squared plus 1. The x-axis and the line x equals 3. Okay. So this is an area problem. And again, I should probably note that all of these examples are also in the textbook. It's just my job to kind of break down every step of them for you, so that if you don't understand something that they show in the textbook, that you'll pick up the missing pieces. So what is this doing here? So let's see. So x equals 3 is like this line here. So 3. What does this function look like? I'll just plot a few points to get a sense. So at 3, what do we have? 3 over 10. So 3 over 10. It's not that high, it's like right there. Maybe it looks like something like that. Maybe. I would definitely, if I had a graphing calculator on me, I would plot this and look at it. Oh, and x is equal to 0. I know that it's 0. So probably looks something like that. All right, if x is 0, it's there. So this is the area that we want to find. Bounded by a graph of this line, and the x-axis. So all of this. So this is a definite integral that we need to solve for. And I erased the rule, but again, what we're trying to do at each of these problems is just apply the theorem 5.5, which says that the antiderivative of 1 over u du is equal to natural log absolute value of u plus c. So we're just applying this theorem in one way or another in each of the problems. So we have to find this area. This is a definite integral problem. The bounds of integration are 0 and 3. That's our function. So the solution is that integral. So we want to evaluate this integral. Okay. So as I mentioned with this problem over here, this example, we want to see if the integral that we're looking at has u underneath u prime, basically. In an informal manner, that's what we're seeking. So if I look at the denominator here, and I take the derivative of that, do I get some form of x? Yeah, right? So if we say u is equal to x squared plus 1, then du, right? Du is going to be 2x dx. Right? Oh, we're getting close, right? See, there's our u in the denominator, right? And then we have x dx. So if I divide both sides by 2 here, I get that 1/2 of du is equal to x dx. So now I can replace everything in terms of x and with u, right? So this integral then becomes so 1 over u, and then dx is equal, so x times dx is equal to 1/2 of du. But something's different now. These limits of integration were in terms of x, not u, right? But u is a function of x. So when x is 0, what is u? When x is 3, what is u? Right? So we have to update these limits of integration. Sometimes when I'm doing these types of substitutions, I will explicitly write x equals 3, x equals 0, just so I can remind myself that I need to change those limits. So can someone tell me what I'm going to write right there? Just take a guess.
1.
1, right? Because when x is 0, u is 1. And then what am I going to write there?
10.
10. Because when x is 3, u is going to be 10. Okay, so now we just have to solve this integral. So this 1/2 business, that's just a constant. I can take that out front. Tells me 1/2 of definite integral from 1 to 10, 1 over u du. Now that looks like that, except for we don't, this is the indefinite form, this is the definite form, so we'll just have natural log absolute value of u in this case. So, log absolute value of 10 minus net log absolute value of 1. I don't have a calculator on me, but I do know something about that. What's that?
0.
0. Natural log of 1 is 0. So this is going to be 1/2 natural log. And 10 is positive, so I can just like not worry about that. So whatever this number is will be that area. Now, this was one way of dealing with these limits of integration by switching from x to u's. Another way would be to, when you get to this step here, you would have natural log absolute value of u. You would go ahead and substitute back in your x's. Do you see that? How it would be the same? Like, I'll write it really fast just so you can see that there's two different ways to do this. So, x equals 0, x equals 3. But now we did the substitution, right? So 1/2 whatever u du, right? So suppose we left the limits of integration at 0 and 3. So then this would become 1/2 natural log absolute value of u evaluated from x equals 0 to x equals 3, right? But then what's u? U is that, right? And you see that when you would evaluate this difference, it would be the exact same as that. So there's two ways to do it. you can switch your limits of integration immediately to be in terms of u, and then you don't have to worry about substituting back. Or you can keep the limits the same and just be sure that you plug into x and not u. Okay. It's really important to understand what's going on. That u is a function of x, right? You can't replace u by that number. You have to treat it how it is. But yeah, so that's the answer there. Okay, another example. Find the indefinite integral of secant squared x over tangent x dx. Okay, I'm going to pause the video and let you try that one on your own for a moment. Now that one's going to probably throw some of you off because it's a trig function.